Okay, let's dive into this. Welcome to today's explainer. We're going to take a journey down into the absolute depths of the ocean to look at a technological frontier that is completely reshaping how we extract energy. We are talking about subsea processing and multiphase pumping. Just imagine taking the massive, sprawling infrastructure of a traditional offshore platform and moving the whole shebang hundreds or even thousands of feet underwater right onto the seabed.
To really set the stage for what we're looking at, ask yourself this: what if we could build an entire oil refinery directly on the ocean floor? It sounds straight out of science fiction, right? But this is the actual bold vision engineers are turning into reality right now. It's a complete paradigm shift for the offshore industry. We're moving the heavy lifting from the surface straight down into the freezing, crushing depths of the ocean.
So the crucial point here is understanding the contrast between the old way of doing things and the new. In the conventional model, well, fluid comes up from the reservoir, travels through miles of subsea flow lines, goes up a riser, and finally arrives at the platform. The platform is where all the processing happens. The seabed is basically just a delivery point. But now, imagine a totally different model. What if we could do the separation and pressure boosting directly on the seabed? What if we could process everything right at the wellhead, before it even starts that huge journey to the surface?
To make sure we're grounded in the terminology, subsea processing is simply the separation of gas from liquids and, crucially, water from oil, directly on the seabed, near the subsea wells. This lets us transport those separated products much more efficiently, or even dispose of them locally. This isn't just a minor tweak, it's honestly one of the most exciting frontiers in offshore technology today.
Part 1. The subsea water problem. You might be wondering, why go through all the trouble of building these underwater factories? Well, it all comes down to one massive logistical headache: water. Specifically, a 90% water problem. You see, as an underground oil reservoir matures, it produces an ever-increasing volume of water alongside the oil. Eventually, an aging well might be churning out 90% water and only 10% oil. That is a staggering 9-to-1 ratio.
Which brings us to a multi-million-dollar question. How on earth do we efficiently transport 9 parts of completely useless water for every 1 part of valuable oil across, say, a 100-kilometer pipeline? It's kind of like paying premium shipping for a giant box of rocks just to get a single diamond at the bottom. The reality is, we can't do it efficiently. Pushing all that heavy, useless water through miles of flow lines, up a riser, and into a topside facility takes monstrously large pipes and incredible pump capacity. It's wildly expensive and incredibly inefficient.
Part 2. Seabed separation and pumping.
So if we can't afford to bring all that water to the surface, the elegant solution is simply to leave it behind. Instead of forcing that raw mixture to struggle all the way to the host facility, we can drop a separator and a multi-phase pump directly on the seabed. We strip the water out right at the source, and then use the pump to boost the pressure of the remaining oil and gas. This way, everything flows smoothly over long distances, without turning into those violent gas slugs that can severely damage equipment on the surface.
The operational benefits of doing this are literally game-changing. First off, we're disposing of the water at the source. It gets cleaned up to strict environmental standards and can either be safely discharged into the sea or re-injected back into the earth to maintain reservoir pressure. Second, because we aren't dragging all that water up, we massively reduce the weight and equipment needed on the surface facility. Third, leaving the water behind means we can use much smaller diameter flow lines and risers, which saves an absolute fortune in material costs. And finally, boosting the pressure early on totally eliminates those nasty multi-phase transport issues over those really long distances.
And the crazy part is, this isn't just theoretical. It is happening right now in some of the most unforgiving environments on Earth. Way back in 2007, the Tortoise Field in Norway launched the world's first commercial subsea separation system. And then you look at Shell's Perdido development in the Gulf of Mexico. They installed separation units at an unbelievable 9,000 feet deep. That's over 1.5 miles underwater, operating in absolute darkness, near freezing temperatures, and totally crushing pressures.
Part 3. Engineering for the deep.
So, how do you actually build a machine to survive down there? You build a subsea separation and injection system, or a subsys module. Housed inside this incredibly heavy, protective steel frame is a super complex array of separators, high-power pumps, pipework, and control systems. We aren't just talking about a simple valve here. This is a multi-billion-dollar, high-tech factory sitting silently on the ocean floor.
The design requirements to pull this off are frankly brutal. First, the whole system has to operate without any human intervention for a really long time. We're talking 20+ years. Second, since humans absolutely cannot dive to these depths, every single component must be ROV maintainable.
That means underwater robots have to be able to fly down with specialized robotic tooling to swap out parts. Third, extreme reliability is key. If a subsea pump fails, production completely stops, and getting a replacement down there takes months. And lastly, the hardware has to survive that insanely high pressure and low temperature environment day in and day out.
Now, these underwater factories obviously need power and instructions to work. They are connected back to the surface by what's known as an umbilical. Think of this as the literal lifeline of the subsea system. Inside this highly engineered composite cable, you have electrical power conductors delivering huge amounts of juice, up to 36 kilovolts just to run the pumps. You've also got hydraulic hoses snaking through to physically actuate massive valves and inject chemicals. And wrapping the whole thing together are fiber optic cables, beaming high-speed control data back and forth to operators miles away.
Part 4. The Future Offshore Field.
As subsea technology keeps evolving, and these umbilical lifelines stretch further and further, the traditional offshore industry is transforming. Experts now predict that the future offshore field may look very different from today's, with most processing done on the seabed and the surface facility reduced to a simple export terminal. Just picture that. Those towering multi-level steel platforms with hundreds of crew members could largely disappear. The real work is going to happen invisibly on the ocean floor, leaving the surface with maybe just a simple buoy to load waiting ships.
And so, as we wrap up this explainer, it leaves us with a pretty massive question. As water depths increase and the subsea technology evolves at such a rapid pace, what is the ultimate limit of underwater automation? We've gone from just piping raw fluid to the surface to dropping entirely robotic, multi-billion-dollar processing plants a mile and a half deep. If the seabed is the new surface, where does it all stop? Thank you so much for joining me on this deep dive. Stay curious and keep exploring.